Okay. All right. All right, you guys. Let's get started. I'm a few minutes behind because of lab. But let's pick up where we left off last Friday. So define chromatography, we did that a couple of times already. So we'll move on to reminding you about what is the difference between stationary phase and mobile phase, and what is the function of each. Let's see if you can remember. Cam.
So for the mobile phase is what like moves along the column.
Yes.
And carry the substance.
Yeah.
And the stationary phase is the one that stays in one.
Yes. So it stays in one place. So you didn't say the function of the mobile phase, it carried the constituents along. So what's the function of stationary phase, Kevin?
To absorb the thing that's being carried, your sample that's being carried. Is it part of? I can't think of the word, but it's a loop, like.
Yes, the eluent, the constituents. Yes, very good. It's the stationary phase is what actually sometimes it's absorbed, but it's not always an absorption. It's what attracts, probably is the better term for it, attracts the different constituents that you're interested in separating in your sample. So basically, the stationary phase has to have some sort of affinity to your constituents, otherwise you won't get separation. So that's why it's very important to select the stationary phase that we know our constituents will have some sort of affinity towards, so we can separate them from each other, identify them, or detect them first, identify them, and then quantitate them if we want to. Okay, good. So list 3 types of chromatography. Types. Reverse phase, that's mode of separation. But reverse phase is correct, but modes of separation. Type. Oh, okay. So do you GC, yes. HPLC, and there's one more we didn't talk about. Does anybody remember? TLC. TLC. Yes, got me there. I didn't. For TLC, I meant to say supercritical fluid chromatography, which we will talk about as well today. So these are the 3 types of chromatography. And TLC is part of LC, Stella. It's liquid chromatography. Yeah, but it's a planar versus column. Yeah. Okay. What is the form of mobile phase in GC? You want to go ahead, Lisa? Gas. Yes. So when we say gas chromatography or liquid chromatography, we're really referring to the mobile phase. So what is the stationary phase in gas chromatography? What would it be? What can it be? Solid. It can be solid. It can also be liquid. Liquid, at least you answered that. You answered. You answered. Yeah. Okay. So if the liquid can be adhered upon a solid, which would be the solid is kind of the support. In that's why sometimes gas chromatography is referred to as gas liquid. Same question, what would be the stationary phase and mobile phase in partition? Do you remember in partition chromatography? What would be your mobile phase and stationary phase? Liquid, solid, gas, integrated power. Liquid. So when you hear the term partition, both phases are liquid. So in the chromatography, which we covered last time, it says partition because the paper is only serving as a support. Okay, so that you can have water adhered on it, and then the mobile phase will be an inorganic or organic solvent that is immiscible with water. What about absorption chromatography? What would be the stationary phase? We already know it is liquid chromatography, so you have mobile phase that is liquid, but in absorption chromatography, what would your stationary phase be? Solid, yeah, yes. Okay, good. What is a partition coefficient? Partition coefficient. It's a constant. When you hear the word coefficient, it's a constant now.
It's how soluble the substance in the mobile phase over the how soluble it is in the stationary.
Correct. So it is the coefficient that gives you the ratio of its partitioning between the mobile phase and the stationary phase. Mobile phase as phase one, stationary phase as phase. Some applications, we talked about a lot of applications. All of you have done an application today and what happened with it. So, please, go ahead.
Well, today in like the GC, we like did qualitative, so we were basically identifying the fat, what kind of fat it is by kind of acid separation. Yeah, but you can also do quantitative by identifying like the exact amount.
Yes, so exactly. So today, some of you did the GC lab, you did semi-quantitative GC where you were looking at the identity of fatty acids so that you can use it for determination of different points. So it was mostly qualitative, has some element of quantitation, but you can do quantitation if you run standard curve, like the other group today in the lab. What did you do? Where is the other group? None of you are here?
Found like concentration.
Concentration of what?
Caffeine.
So an example is used to determining the caffeine content in beverage. And we give a lot of different applications, and they come throughout the lectures this semester: carbohydrates for small sugars detection. So we do for amino acid composition, we do flavor analysis, we do contaminants of concern, we do vitamins, a lot of application for GC and LC, and we'll see that throughout the semester. And that's why we're learning about chromatography as a base before we go into applications. All right, so we were talking about paper chromatography and how components separate, and the way to measure, to have kind of a quantitative measure, is we determine the relative mobility factor, which is basically you measure the distance that a component has traveled. So you take, like, you look at a spot and you measure the distance between where you spotted your sample to where you see a physical spot, you take to the center of it. And then you measure that distance, and then you see how far your solvent traveled. Let's say you let it develop for 10 centimeters or 10 inches, whatever your measurement is. So you measure that, and then you get a relative mobility. So you would have run your standards. You will get the relative mobility of your standard compound, and then you have the relative mobility of your actual compound in the sample. Then you try to use that to identify. Our F values, that is the relative mobility factor values, usually they are constant, but they are impacted by the thickness of the paper, the time of the development. There might be a few seconds difference in the development time. So therefore the distance will be different a little bit, the humidity in your chamber, and the temperature, because with higher temperature you have faster movement. All right, so it's supposed to be constant, but maybe it's impacted by so many different factors. So the paper chromatography we talked about is normal phase. We said you have a cellulose paper and impregnated with water. So that makes it polar stationary phase and non-polar mobile phase, that's normal phase. It can be the opposite, where the support is impregnated with non-polar solvent, and then you develop with water. So that makes it reverse phase. So normally paper chromatography is normal phase, but if you really want to run it on the reverse phase, you can. And the reason you choose reverse versus normal is based on the components you have in your sample and how you want them to separate. It can be ion exchange, it can be absorption chromatography, where it's a solid and the OH groups on the cellulose are ionized. So they are derivatized with an acid or a base functional group to make it carry a negative or a positive ion, so that you can separate positively or negatively charged compounds. All right, let's check your memory here a little bit. In reverse phase, paper chromatography, the most polar travel the most. The least polar travels the most. RF value of the polar compound will be higher than the less polar one. Think about it, all of you. I want to see a few hands up, not the same people. Get alive, people.
A and C.
A and C. Thank you. And you're Taylor, right? Yeah. Good. You don't talk much, Taylor, but I remember you. But when you talk substance. So this is correct. Okay. So the most polar travels the most with water. If it's reverse phase, then your mobile phase is polar. So it travels the most with the polar. And then the RF value will be higher because it travels the most. So you will have more distance covered than the less polar one. Okay. TLC. I like to tell this story. Every year I tell the same story. My TAs are bored of it, but I still find it entertaining. When my daughter was little, there's always examples with my daughter involved. So when my daughter was little, like 3-4 years, she was in preschool daycare. So I went one day after teaching lecture on chromatography, I went to pick her up, and she was sitting in the teacher's lap. And then I said, what happened? And she said she needed TLC today. And in my mind, why would she need thin layer chromatography? And then they said tender love and care. And that's when the first time I learned about tender love and care. So TLC is for thin layer chromatography and for tender love. So it has similar properties to paper chromatography. It actually was developed to replace paper chromatography because of different functions. So it has better resolution. Again, when I say resolution, what do I really mean by resolution? I want you to learn this term. Better resolution. Better, what's the definition of chromatography? Separation. Yeah, very good. So I have better resolution of two compounds, better separation of these two compounds. Because when we use thin-layer chromatography, we have material with very small particle size, smaller than the particle of the paper. So then you have more uniform particle size across the surface. Then we have, with that, we have faster movement of the solvent and the constituents. And we have better reproducibility. We run it the same sample multiple times on different thin layer chromatography plates, then I'll get similar results or similar what we call RF values. So basically you have a solvent. And most common it is silica. Silica is what we use most commonly. It can be alumina and cellulose, but you use silica on a very sturdy support, either glass, plastic, or aluminum foil. So glass was mostly in the olden days, like when I was an undergraduate student, we used to get glass plates and clean them really well. And then we used to put a very thin layer of silica on top of the glass. Apply that, make sure it is thin to a specific thickness and uniform. But nowadays you can buy them as aluminum foil with silica already plated on them, much better than you doing that yourself in the lab. So they're cheap, they're easily available, abundant, so no issue there. You can use them same as with paper. You can use them as normal phase, reverse phase, ion exchange, chromatography. So there are specific chambers for thin layer chromatography, and you put about a 1 centimeter space, and then you spot your sample 1 centimeter from the edge, and you put your plate in a chamber, and you put your mobile phase, and then you let it develop over time, and then you would measure or qualitatively mostly, and you can do some quantification. The way to see the spots, the saline hydride for amino acids commonly used, gives you colors. What you see here is a fluorescent. So this is fatty acids and other types of fats. So you have phospholipid, monoacylglycerol, diacylglycerol, fatty acid, triacylglycerol as standards. And then you have your samples. And you can see in your sample what components you have in there. Okay, and this is qualitative, but you can do sometimes quantitative analysis. You can actually look at the density of the spots using a densitometer, and you can take the density of the standards, get the calibration curve, and be able to semi-quantitate your samples components on the plate itself. You can scrap it off, dilute it, put it in a clean, we call it some cleaning resin, small column, small syringe, pass it through, clean it from other constituents, and then use a different method to quantitate. So you can do that, but often we'll see when we cover, let's say, pesticides, it's used as a screening method. You don't necessarily use it for quantification. So it's mostly a screening method. They use it, for example, if you're doing minor nutrition or double mingling, you will take experimental nutrition lab. They use it to measure the different components of fatty acids and triglycerides and what have you in the blood. Okay, so now that you have an idea about planar chromatography, like I said, paper chromatography is phasing out, thin layer chromatography is used as a screening method, but for any fractionation and identification and quantification, it's mostly liquid, column liquid chromatography. So we're going to spend quite a bit of time describing column liquid chromatography. I usually bring with me columns, and today I was running to get here on time and I forgot to bring in my columns. We have different types of columns that we use in column liquid chromatography. We have the low pressure system and we have the high pressure system. The low pressure system is basically glass columns, big, round, mostly glass. There's plastic, but it's mostly glass columns that we fill ourselves with media. And we run our samples under low pressure because it is not packed as a column that we usually with high performance chromatography. They generate a lot of back pressure. Since it's not tightly packed, the low pressure liquid column liquid chromatography, column liquid chromatography using those big columns generate low pressure. And that's why we call it low pressure liquid chromatography. So, but this is a scheme that shows a little bit what happens in column liquid chromatography. So you have your column that is packed with your media, which is your stationary phase. And then you have your mobile phase in a container. And you need some sort of a pump. Okay, the peristaltic pump is for low pressure chromatography. Sometimes you have two mobile phases that you mix together. And then they get pumped onto the column. There should be a tubing for injection where you inject the sample that sits on the top of the column. And then the mobile phase is going to go through, and the sample constituents are going to start all together up. And as they go down, they're going to start separating based on their affinity to the stationary phase. So that you get separation. And if we look at this route, you get separation, and hopefully if you get good resolution, that is good separation, you get each constituents alone. You have a detector, in this case UV detector, but there's so many different detectors we'll talk about in the HPLC lecture. An absorption is measured, refractive index is measured, light scattering is measured, something is measured here, and then you get a signal that you would see in your software as a chromatographic peak. So basically, you will get absorption over time in this case, or refractive index over time, and you get a peak for each compound. Then you can do detection with standards or detection with a powerful unit like a mass spectrometry. After the detection, it can either go to waste, that's it, you detect it, or you collect fractions. When you use this low pressure liquid chromatography, it's mostly to collect fractions in larger amounts. So you will be collecting fractions at different time points to take those separated compounds and do further analyses with them. So you will often have a fraction collected. Sometimes here you have a valve where some of the constituents go to the detector, some of it goes somewhere else to do analysis on it. Let's say you're separating a particular compound and you want to determine its concentration using an enzymatic assay. So you get the compounds, which might be a substrate to the enzyme, and then you add reagents, you have the activity of the enzyme, and then you plot the activity of the enzyme of the different constituents, substrate. Let's say you have different proteins, and you have a digestive enzyme for the protein. It will digest them differently. The protein will be different substrates. So then you will get activity for each individual protein you're separating. So that's an example. Now, from here, what I want you to learn is a few things. We already talked about what stationary phase versus mobile phase. Does anybody have any confusion about what the stationary phase is and what mobile phase? We're good to go. You know this knowledge. Okay. Column dimension. That's when I say I should have gotten my columns with me. So columns can be very long and thin, or can be short and wide. So you have different diameter, different length. We talked about columns that are long, you get really better resolution because you have more time for separation, more interaction with the column. So the longer the column, the better is the resolution. Okay. The narrower the column, the shorter the time and also the better resolution. So you get faster equilibrium between stationary phase and mobile phase. You get really nice sharp peak. So narrow and long, you get really sharp peak, very well separated from another peak next to it. So you have really good resolution. And that's where I have to admit that you have much better resolution in GC than else. So I don't know if Gary told you this, but he really likes GC more than else. Was that yes? Is that okay? All right. So, but GC columns are really long, very narrow pillars. So you have really nice sharp peaks, very good resolution, very high sensitivity, and then very, very low threshold. Because it's really long column, very, very thin layer of stationary phase, you have very quick equilibrium, great resolution. But of course, GC is not good for everything, that's why there's alpha. All right, so, but the idea that I want you to get is that longer column, narrower column, you get good resolution and good separation. Well, resolution and separation are equal. Now, however, it takes a really long time and for the analyses. And sometimes if you really want to get fractions that not necessarily are very pure, but let's say I want to separate carbohydrates from protein. I don't care about separating the individual proteins, for example. I just want to get the protein separated from the carbohydrate in my system. I use very, very short column, very, very wide column, so I can load a lot of sample. I don't care if my peak is not sharp, it just separated from my carbohydrate. So I collect all my proteins, even if they're not very well separated. I don't care. I care for quantity. I don't care for resolution in this case. So depending on the purpose of my experiment, I would select my column. Depending also on the availability in my lab, sometimes I have to select from what I have. But so just these things I want you to remember when you think about column dimension. So packing of the column. So when it's low pressure liquid chromatography, we are packing the columns. We basically prepare the media in a slurry, and then we pump it in under specific pressure, specific rate, and we pack our column. You don't really need to know how to pack the column unless you have to pack the column for research, and then you follow instruction that comes with the media. So not to worry about that very much. Now, the other thing I want you to remember is two terms: isocratic versus gradient elution. Isocratic, what does it mean to you when you hear the word isocratic? Do you have any meaning of it? My phase is constant. The mobile phase is constant over time. It does not change. So if I start with water, it's water throughout my run. If I start with an organic solvent, acetonitrile or methanol, it is methanol throughout the run. I don't change anything. It's isocratic mobile phase. I use a lot of isocratic in, let's say, things like size exclusion chromatography, where really there's no interaction with the media, there's separation based on size, so my molar phase is isocratic. I use isocratic if my analysis time is short and I'm getting everything separated. I do not need to increase the power of my molar. Oftentimes, though, I need to use gradient dilution. Those of you that did PNC today, we did gradient dilution. What does it mean to use gradient dilution? Those that did the lab today,
like the concentration of the normal phase, or not the concentration, but
Yeah.
the strength of it is going to fluctuate throughout the.
yes, exactly. So the concentration or the strength is going to change over the analysis time. So I'm changing the composition of my mobile phase. That's when I have 2, 3, or 4 solvents here that I need to mix throughout my run. Sometimes it is, mostly it's 2, but sometimes it's 3, sometimes it's 4, where I have to change the composition of the mobile. Now, the other term that's not there that will show up later on is increasing the strength of the mobile phase. That's when we are running a gradient in solution, that's what we do. We're increasing the strength of the mobile. Again, I bring you back to the example of the justice with me and my daughter. So we separated very quickly because she's interacting with the stuff in the store. But if she's interacting strongly, there's nothing that's gonna let her off, or maybe it's gonna take her a very long time. So I bought her something, she left the store. So the same idea with the stationary phase, with the mobile phase being gradient, is if you have like your caffeine molecules interacting strongly with the column, it's moving very, very slow with the mobile phase that is mostly water. It's just moving, it will come out eventually. Maybe it's going to take 12 hours to come out. I don't have 12 hours to do the analysis. So I increase the strength of the mobile phase. How did I increase the strength of the mobile phase in there today? Do you remember? What we did? We're doing the allergies. Oh, sorry, it's okay. There.
By changing the ratio of water.
Yes. So what did I do with this?
You would, increase.
I increased the concept thought, sorry, you guys, when I thought you were with us. Okay, so we increase the strength by, if I'm running a reverse phase chromatography, I start with water. Caffeine is going to interact with the non-polar state. If I want it to come out sooner, leave the column sooner, I need to give it something that the caffeine would like more. So I increase the acetonitrile concentration. So I'm making my mobile phase stronger for the caffeine, so that the caffeine will move faster through the column and elute, come out faster in 15 minutes rather than 12 hours, for example. Increasing the strength of the mobile phase is not always in one direction. So I don't always increase acetonitrile. So sometimes if it is normal phase, I'm starting probably with 100%, 99% acetonitrile. How do I increase the strength over time of a normal phase? You guys are tired, it's still Monday. What will you look like on Friday? You just, where's your energy? Okay.
It's just the opposite.
Yeah. You increase what? The water. So it's not always in one direction. Increasing the strength does not mean increasing the solvent, the organic solvent all the time. It depends on what your stationary phase is and what your mobile phase is. So keep that in mind. When you say increase the strength, it's not always increasing acetonitrile or organic phase. Okay, so just remember that. All right, supercritical fluid extraction. So very briefly, I want to go over it. We don't have an application in that for this technique, but it is a technique that is used often for non-polar molecules that are non-volatile and that are thermally labile. That means they can degrade easily with heat. So we cannot use GC for these non-polar compounds. Or it might need derivatization, it might take very long time to get it through the GC. So what we do is, instead of using the GC, we get CO2, which is gas, but we put it over a critical pressure and temperature so that it becomes liquid. So liquid CO2 have really high, it has really high diffusivity and has very low viscosity. So you get really good resolution in a shorter period of time. So it moves really fluently and gives you good resolution. The stationary phase is very similar to the phases that we're going to describe for high performance liquid chromatography. And also, the equipment is similar to high performance liquid chromatography, but the detector used are similar to those you covered for GC. So for GC detector, so you can have an FID, for example, chemization detector could be used in supercritical fluid. So that's all what I need you to know here about this type of chromatography. All right. We're going to dive deeper into column chromatography and talk about the different modes of separation. So Lisa, you said reverse phase, answered the question earlier. When I say what's the mode of separation, I would be looking for you to tell me, is it adsorption, is it partition, is it site exclusion or molecular exclusion? It means the same thing. Sometimes we hear gel elimination. This means the same thing as molecular exclusion chromatography. Is it ion exchange? Is it affinity chromatography? These are modes of separation. So it's not types of chromatography, it's modes of separation within liquid chromatography. Okay. They can be color liquid chromatography, they can be paper or chromatography plan, but we're going to talk from here on about color liquid chromatography, and these are specific for LC boundaries. Okay. And then we're going to start talking about different physical chemical principles behind these different modes of separation or chromatography modes of separation. One thing I want you to remember is ion exchange and affinity chromatography are part of adsorption chromatography. Okay, there is also, that is not depicted here in the picture, is the hydrophobic interaction chromatography, which is also part of adsorption. All right, so this is a very good figure. You have it in your chapter as well for trying to visualize the principles of separation, principle behind separation. So in, does this always show up at the top? Is this always there? Yeah. Oh, okay, the stop share and all of that. This is the first time I noticed, okay. So your components in adsorption chromatography adsorb to a solid phase. So they adsorb, but not irreversible adsorption. It is always reversible adsorption. So the molecular interactions are not covalent. So you have to remember that in order to get separation, you need to have interaction in the stationary phase, but the interaction is not covalent, because if it's covalent, it would be almost permanent. So your interactions are via non-covalent molecular interaction. So these components or constituents are going to adsorb on the functional groups of your solid stationary. This one we talked about already. You have an impregnated, sometimes it's chemically bonded to a support. A very good support. And then it's a liquid. So your stationary phase is liquid, and then your mobile phase is liquid, and then your solute is moving in and out based on its solubility in each of these phases. Okay. So it will partition, and that's what it's called partition chromatography. It's going to partition between two liquids based on its solubility in each of these components. Then you have the ion exchange, which we will spend time talking about. You have, in this particular example, it's anion exchange. Anion stands for negative charge. But you're going to say, oh, but it has positive charge on its stationary. Yes, it has positive charge, so it's going to attract to a negatively charged compound. That's why it's called anion exchange. We are exchanging between the stationary phase and the mobile phase. What is exchanging is these negatively charged compounds. Okay? So that's why it's called anion exchange. It is positively charged stationary phase exchanging, attracting negatively charged ions in my sample. So I am exchanging negatively charged compound. We'll talk about the principle of ion exchange. It can be anion, it can be cation as well. So there are two types, cation and anion. In this picture here, we are picturing an anion. All right, and then you have the molecular exclusion, like I said. You will hear it or see it, size exclusion, molecular exclusion, gel permeation, they all mean the same thing. So here you have particles that have different pore sizes. And then you will have, in your sample, you have components of different sizes, different molecular weight. They're going to separate based on their size. Those that are small are going to go in all the pores. Those that are big might be prohibited from going into some pores, so they will travel faster. So in size exclusion chromatography, the larger molecules are going to move very, very fast because they can't go into the pore sizes, the different pores. The small ones are going to take their time, sweet time, going in and out, and going in every pore possible. So they'll take the longest time to be calm. In affinity chromatography, it's the lock and key kind of thing, if you want to remember that. So it's very, very specific interaction. So you have, let's say, an enzyme inhibitor here as your ligand, we call it ligand, on that stationary phase. And you have enzymes, mixture of proteins, and you want this particular protein that is an enzyme to separate from all of the other junk that you have in your sample. So then it will bind very, very specifically. Everything else will you to come out. After everything else comes out, you change the mobile phase. You enhance or increase the strength of the mobile phase in such a way that these will unbind become unbound. And the way to change that, you can change the pH. You change the ionization, so they will no longer interact. You can change the salt concentration. Then they also will change the charge on that. You can put an enzyme inhibitor in the mobile phase itself. Then it will interact with the enzyme inhibitor in the mobile. So then you can get it out. Okay, so this will serve as a review, a visual review of the different phases. Okay, that was a stop, but I have a couple of minutes, so I was going to go over absorption chromatography, where you have a solid phase and the stationary phase that is the absorbent, mostly it's a solid, and then your mobile phase is liquid. And then you have interactions, like I said, non-covalent. Molecular interactions that are non-covalent. They can be hydrogen bonding, they can be ionic, like electrostatic forces. They could be van der Waals, they could be hydrophobic interaction. So you will have some sort of reversible interaction. If you don't have an interaction, you don't have a separation. You have to have some of your components interacting with the column in order to have a separation. Here in absorption chromatography, the coefficient is not constant. Partition coefficient is constant because you have a liquid and a liquid, and the compounds partition between the two liquids. And if you get to a constant, absorption coefficient is not a constant. And in this case, how much sample you inject on the column is very important. You have a term that we call overloading. You don't want to overload. Because you have very specific functional groups on your column, a number of them. A certain number based on how big the column is, how wide, how tall. There's a specific amount of stationary phase in there and specific functional. If you put a lot of sample, you will block all of the functional groups. And you have some that have no room, will leave the column without interaction. You get very poor resolution, make messed up chromatography, because you don't have a constant absorption coefficient. Because there is a limit, there is a capacity. I'm going to talk about capacity later. You do not want to exceed the capacity of your column. Okay, so that's something for you to remember as well. All right. I can stop here. I will see you on Wednesday.